Hello, and this video is on lesson 4-1, page 57, where we talk about introduction to piecewise-defined functions. Now, I thought it would be really useful to just go over some ideas that we covered in the past lessons. So if we have less than or greater than, you're going to use an open circle when you graph it on the line. And your line is going to be dashed or dotted. If we have less than or equal to or greater than or equal to, our circle is going to be closed and we use a solid line. Now another thing I thought it would be useful is to graph both of these inequalities. So let's go ahead and read the first one. X is greater than or equal to 3. Since we're talking about x and we are on the xy plane, we're going to locate 3 on the x-axis, and notice that we have greater than or equal to, which means we're going to use closed circle. And since we are in an xy plane and not just on a number line, that means that our line, since we're talking about the x-axis, if our point is on the x-axis, we use a vertical line. So we are on the x-axis, we are using a vertical solid line since we have less than or equal, greater than or equal to. Okay. So x-axis, yeah, use the vertical line. If you are on the y-axis, you have to use a horizontal line. Okay. Now what we need to do is figure out which side am I going to shade on, the left or the right side. Well, all you have to do is just simply read this. X is greater than or equal to 3. What numbers are greater than or equal to 3? Well, greater than or equal to 3, well, that's 4 is greater than or equal to 3, 5, 6, 7, and so on. So our shaded area is going to be on the right side of the line, the solid line. And I'll try my best to graph this on the right side, just the right side. So it looks something like this. Yep, that's the best I could do. Alright. Now here we have x is less than 3. Again, we're still on the x-axis, and notice we have just less than. So if we have less than, I'm going to use an open circle and a dashed line. Now, since again I am on the x-axis, it's going to be a vertical line. So here's my open circle at 3. It's going to be a dashed vertical line. Alright, now here comes the question, what side am I going to shade on? Well, just read the inequality. X is less than 3. What numbers are less than 3? 2, 1, 0, -1, and so on. So that means I'm going to shade on the left side using a different color. There we go. There, that's better. Alright, so those are the inequalities. Yeah, the inequalities as we solve them. Now, in order to begin understanding piecewise defined functions, we're going to look at just a very simple example before we get into the lesson. Alright, now let's go ahead and read this one. Y is equal to 1 over 4 x plus 1 for x is greater than 0. Now, something very important here that I need to point out. I am going to graph this equation, not this inequality. So notice in the past two examples I graphed the inequalities, but when you have an equation and then for x greater than 0, you're not graphing this inequality. So if I'm not graphing it, then what do I need it for? Why is it here? Well, let's go back to our other two examples. Now, what I showed my students is I said that since we're graphing on this side right here, then just think of a wall right here. There's a wall right here blocking any solutions from going to the other side of that solid vertical line. And here there's a wall right here blocking the solutions from being on the right side of that vertical dashed line. So as you can see, the wall blocks the solutions from going through the other side. And so basically we didn't need the wall here. We were able to graph our inequalities, so we didn't need the wall. But once we get into questions like this, we definitely need to see the wall is going to help us find how to graph this type of setup right here. So let's start by thinking of graphing this inequality. Assume we are graphing this for x is greater than 0. So we are on the x-axis, and I have my open circle here at 0. And since I am on the x-axis, I'm going to draw a vertical dashed line. Now we have to figure out what side, left or right, are my solutions going to be shaded on. Well, just read this. X is greater than 0, so that means I'm shading 1, 2, 3, everything to the right side of that line. Those are where all the numbers are greater than 0. Which means that my wall, when I draw it, is going to be on the left side of that line, because it's going to block any solutions from being graphed on the other side. So that means I'm only graphing on the right side of that line, vertical dashed line. So let's go ahead and try to graph this. Y is equal to 1 over 4x plus 1. Well, there's so many ways that we can graph this, and I was glad that some of my students were able to realize that you can use y equals mx plus b, where 1 is going to be my y-intercept. So notice I have 1 here, and because it is a dashed line, and because we have the inequality greater than, I'm going to have to use an open circle, because it falls exactly on that wall. Whenever you have points exactly on the edge of the wall, you have to determine if you have open or closed circle. So we do have an open circle here. And so the y-intercept is 1. The slope is going to be 1 over 4, which is the rise over run. So I was really glad that some of my students were able to explain this to me. You just start from the y-intercept, go up 1, and run over 4, 2, 3, 4, 1, 2, 3, 4, and so on. Now, notice I can just keep on graphing the rise over the run, and I can just keep going to the right. And so if I can keep going and never stop, I can represent that with an arrow. So the arrow means that the line just keeps on going. But when I go to the left, notice that I hit that wall. And remember, I can't go past the wall. And so that is how my line is going to end up with. So when I take that wall away, here is my graph. This is what we graphed. We graphed y equals 1 over 4x plus 1. And this right here, that's called a domain restriction. It told us where exactly the wall is, where where is the only place that we can graph? Well, it's only on the right side of the wall. Anything beyond this vertical dashed line on the left side is we can't touch. We can't graph there. Alright, so this is an important concept which will take us to lesson 4-1. So the learning targets are to graph piecewise defined functions, write the domain and range of functions using interval notation, inequalities, and set notation. Alright, let's begin. On the top of the page it says, the graphs of both y equals x minus 2 for x is less than 3 and y is equal to negative 2x plus 7 for x is greater than or equal to 3 are shown on the same coordinate grid below. Number 1 says, work with your group on this item and on items 2 through 4, describe the graph as completely as possible. So my guiding question was, how would you describe the graph above for someone who can't see it? Number 2, why is the graph a function? And my guiding question is, how does the graph pass the vertical line test? So notice, let me write this out. Here is, we'll call this the first function rule, y is equal to x minus 2. For our domain restriction is x less than 3, and y is equal to negative 2x plus 7. For the domain restriction is x is greater than or equal to 3. Now notice, again, similar to what we have here, we have our function rule and a domain restriction. So to determine where to even begin how to graph this, to determine where our wall is going to be at, we have to look at domain restriction. For x is less than 3. So right at the x-axis, I'm going to have an open circle at x equals 3. And I'm going to draw a vertical dashed line. Now, which side of the graph am I going to, which side of the line, am I going to graph this function right here? Well, for x is less than 3. What numbers are less than 3? Well, it's going to be 2, 1, 0, negative 1, negative 2, and so on. So notice that instead of creating a wall like we did here, right here, what I'm going to ask you to do is to draw the wall as a vertical dashed line. So notice it's already graphed here, y is equals to x minus 2. This is the graph right here. And notice that it keeps going to the left, and so they did draw an arrow. But once it hits that wall, you notice that it stops. It doesn't keep going as it would like this. It stops exactly when it hits that wall. Alright, let's take a look at the second function rule. So here's our function, and here's the domain restriction. Now let's go ahead and read that. Again, we have let's read this. We have x is greater than or equal to 3. So right at my x-axis, right at 3, I'm going to draw. Now I know I said to use closed circle and a solid vertical line, but since we're talking about graphing walls, not inequalities anymore like we did here, we're not graphing our inequalities, we're just graphing the wall. And the wall is always going to be represented by a vertical dashed line. So very important. Wall is a vertical dashed line. But what this tells us is if we're going to shade on the left or the right side of the wall. So for x is greater than or equal to 3, that means I'm going to shade for numbers greater than or equal to 3, which is 4, 5, 6. That means I'm going to shade on the right side. So this is going to be shaded on the right. This is going to be shaded on the left. And as you can see, it's already graphed for us. And notice that it keeps on going to the right. It keeps on going to the right, and so they did draw an arrow. But once when you go to the left, once it hits that wall, it doesn't keep going like this, like it normally would. It stops. So as you can see, the graphs cannot continue going past the wall. Once it hits that wall, that's where it stops. Just one simple idea here. Does it pass the vertical line test? Well, let's go ahead and draw a vertical line. And some students were able to remember what the vertical line test meant. If you drag this vertical line across the graph, if it only intersects at one point, then it is a function. If it intersects at more than one point, it is not a function. So as you can see the graph only intersects at exactly one point everywhere. So this is a function. Alright, now we begin graphing piecewise defined functions. So here we have y is equal to x squared minus 3 for x is less than 0, and y is equal to 1 over 4 x plus 1 for x is greater than 0. Now notice in the previous example we had the domain restrictions both included the number 3, and so that's very common for domain restrictions. They're always going to include a pair of numbers that are the same, and so wherever you see the common number, that's where the wall is going to be at. So if we write this side by side, y is equal to x squared minus 3 for x is less than or equal to 0, and we have y is equal to 1 over 4 x plus 1 for x is greater than 0. Notice here again we have the common pair of numbers in our domain restrictions, and so just by looking at the pair, that's right on the x-axis, that's where we draw our vertical dashed line. That's where the wall is going to be at. So here my wall is actually going to be at x equals 0, and I draw that vertical dashed line right there. Now here's what we have to figure out. This first function rule, am I going to draw that on the left or the right side of the wall? So again, we need to look at our domain restriction. For x is less than or equal to 0, what numbers are less than or equal to 0? Negative 1, negative 2, negative 3. So they lie on the left side of the wall, and so we're going to graph this on the left. Looking at the domain restriction for the other one, here we have x is greater than 0. Well, the numbers 1, 2, 3, 4, 5, those are greater than 0, and so we're going to graph this on the right. Alright, let's go ahead and begin. Now, I recommend that you actually create a table in order to graph these. So if we create our table, we have our x, and we have our f of x. And since our graph begins at -6, -5, and we'll just continue all the way to 6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. Alright. Now, once you create your table, you have to figure out, am I going to take all these numbers here and plug it in for this function or for that function? Well, you're going to have to look at your domain restrictions. Again, looking at the domain restrictions, x is less than or equal to 0. Well, what numbers are less than or equal to 0? Well, that includes 0 and all the numbers below 0, or all the other negative numbers. So these numbers I'm going to plug into the first function rule. And if we take a look at the other function rule, we have x is greater than 0. Well, what numbers are greater than 0? That's going to be 1, 2, 3, 4, 5, and those numbers I'm going to plug into this function. Alright, so again, let's begin with the negative 6. If we plug in negative 6 into for x, we get negative 6 squared, which is 36. 36 minus 3 is 33. Can we graph that? Nope, that's off the grid, so we need to just put that there. We can't graph it. If we plug in negative 5 in for our first function, negative 5 squared is 25, minus 3 is 22. Again, we cannot graph that. So let's continue going until we can find something we can graph. Negative 4 squared is 16. 16 minus 3 is 13. Negative 3 squared is 9. 9 minus 3 is going to be 6. So look at that, we can graph that. So here is our first order pair. Negative 3 and up 6. There we go. Negative 2 squared is 4 minus 3, which is 1. So there's our second ordered pair, negative 2 and 1. Negative 1, 0. Negative 1 squared is 1 minus 3. 1 minus 3 is negative 2. So we have negative 1, negative 2. And then finally, we have 0. And you notice that 0 falls exactly on the wall. 0 does. So that's it, right exactly on the wall. That's where we have to figure out if we have open or closed circle. So let's go ahead and plug in 0. 0 squared is 0 minus 3. Well, that's negative 3. And when we take 0, negative 3, we're going to have a closed circle. There we go. And so those are our points. Now notice that y equals x squared minus 3 is in the shape of a parabola, so it is going to be a curved line. When we connect those points, our graph should look something like this. Trying my best here. I guess that's better. Now, can we keep on going to the left? Yes. We have negative 5, negative 6, and we can go up to negative 7. So we draw an arrow, which means that we can continue plotting points, finding our input, putting our input, and getting our output. But notice, once it hits that wall, we have a closed circle. How do we know we have a closed circle? Because we have less than or equal to, which is the domain restriction of the function that we just graphed. Alright. Now we take 1, 2, 3, 4, 5 and plug it into the second function rule. So let's go ahead and begin. We have negative 1, our input. We have 1 as our input. 1 times 1 over 4 is 0.25. Plus 1 is 1.25. Let's see what other numbers we can get here. So if we plug in 2 2 times 1 over 4 is 1/2. 1/2 plus 1 is 1.5. Okay, I think I can graph that one. So here we have 2 and 1.5, which is right here. 3. 3 times 1 over 4 is 3 over 4, which is 0.75. 0.75 plus 1 is 1.75. If we plug in 4, 4 times 1 over 4 is 1. 1 plus 1 is 2. Well, you can use your calculator, by the way, to help you out, to help you fill this table out. So we have 4, 1, 2, 3, 4, and 2, which is right here. And as you can see, if we continue on going to, let's do our last one. Let's change the last one from 5 to just 6. So we plug in 6, 6 over 4 simplifies to 3 over 2. 6 times 1 over 4 is 3 over 2 plus 1. Well, that's 1.5 plus 1, which is equal to 2.5. So we have 6 and 2.5, which is right here. And when we connect those lines, notice that I can keep going and using more inputs greater than 0, and I draw my arrow to represent that. I just keep on going and going. I can go 6, 8, 9, 10, 11 all the way. It just never stops. But when I draw this line on the left, eventually it's going to hit that wall at some point. Where exactly is it going to hit the wall? Well, notice that it hits the wall when it reaches 0. So if you want to be really precise, you can plug in 0 in for x. 0 times 1 over 4 is 0 plus 1. So our ordered pair is 0, 1. So it's going to hit the wall right here. But that point is not on the wall because we use 0 for, we plug 0 in for the other function rule. But it is going to be an open circle there. So can you see what we're doing here? We're graphing these lines. They can't go past the wall. But once those lines hit the wall, we have to determine what type of circle they're going to be. Here we have a closed circle because we have less than or equal to. Here we have open circle because we have greater than. And so this is going to be how I graphed my piecewise-defined function. That's how you graph a piecewise-defined function. Now, let's take a look at this question. Why is the graph a function? Well, let's use the vertical line test. When I drag this vertical line, is my graph going to intersect at only just one point? It seems like it, but then when I moved it here, students said that it intersects at 2 points here. But some students were able to realize that it only intersects at 1. How is that? Well, realize that here we have a closed circle, which means it's touching the line, the vertical line. But here we have an open circle, which means it's not touching the vertical line. So right at this, when I drag my vertical line here, it's only intersecting at just 1 point, which is right here at this closed circle. So as you can see, this graph this piecewise defined function is intersecting at only one point. Therefore, it's only intersecting at one point everywhere I drag the vertical line. That means that it is a function. And now we formally learn the setup of a piecewise defined function. The functions in items 1 and 3 are piecewise defined functions. Piecewise defined functions are written as follows, using the function from item 3 as an example. So instead of writing it like this in where it gives it to you in a sentence, here's a more compact way of writing it out. Here we have, notice that even though it seems like we have two functions, both of these are counted as just one function. Can you see how it is just one function because it passes the vertical line test? It does not intersect at more than 2 points. So wherever this function stops at, the other function continues on the other side. So it is, we're not counting this blue line and this purple line as individual graphs. They are together counted as one single graph. And so that's why we just give it a single name, which is f of x, followed by a brace. And these individual functions, well, we call them function rules. And here are the domain restrictions. So let's read this box. A piecewise defined function is a function that is defined using different rules for the different non-overlapping intervals of its domain. So there's the key word right here, non-overlapping intervals. Can you see how this function, as soon as it hits the wall, it doesn't go over to this side, or else it would overlap and it wouldn't be a function. So it stops right at the wall, and the other function continues where the other function left off, but using a different function rule. So that's the key to piecewise defined functions. They don't overlap in the intervals of its domain, or else it wouldn't be a function. Now here, this is again similar to what we did with number 3. First of all, the first thing you want to do is look at the domain restrictions. Can you see that these pairs of numbers are the same, -1, and that tells us where the wall is going to be at. It's going to be right here. We represent the wall with a vertical dashed line. So here it is. And now we have to figure out which side of the wall is each function rule going to be graphed on. All you have to do is read the domain restriction. For x is less than -1, well, the left side is less than -1. And also notice that less than -1, which numbers here are less than -1? Well, it's going to be -2, -4, and we can continue going to -5, -6. And so when you graph this line, do you want to use red here? When I take my inputs, these inputs right here, I'm going to input them into the first function rule. And I'm going to take my second function rule and read the domain restriction. It's called x is greater than or equal to (-1). Well, the numbers greater than or equal to (-1) are the numbers on the right of the vertical line. And so when I'm plotting, filling in my table, I take the numbers greater than or equal to (-1). So notice we are also taking (-1), 0, 1, 2, and I'm plugging this into the second function rule. So we can actually do this really quick. I'm not going to fill in the tables because I'm just going to use y equals mx plus b. So if I were to graph this, let's start with x plus 3. X plus 3 will my y-intercept, not that one, my y-intercept is going to be at 3. And my slope is 1 over 1. So if I rise 1, run over 1, I'm going to rise 1, run over 1. And notice that I can just keep on going. There's no wall on the right side. And so I draw an arrow at the end. And now, eventually it's going to hit the wall. And it looks like it's going to hit the wall at y at (-1, 2. So I have to figure out, once I hit that wall, am I going to have an open or closed circle? Well, it's going to be closed circle because I have greater than or equal to. So I draw a closed circle. Now, when I graph this, it can be a little bit tricky because the first thing I would do is just find the y-intercept. But notice the y-intercept is on the right side of the wall, and I want to graph this on the left. Well, you can use it as a guide to show you how your line is going to look like, but just make sure you erase it later. So here's my y-intercept, and my slope is going to be (-2 over 1. So that means I'm going to not rise, but go down to and run over 1. Go down to run over 1. But if I continue doing that, I'm going on the right side of the wall. So I want to do the opposite. So if I continue this trend, I'm going to go up 2, run over 1 to the left, run up 2, run over 1 to the left, run up 2, run over 1 to the left. And you can see how my dots are going to connect like. So when I connect these dots, notice I can keep on going to the left. There's nothing blocking me from going to the left, so I just draw an arrow there. And notice that I'm going to hit the wall right at x equals (-1). Here's where I have to figure out if I have open or closed circles, which this shows I have less than, so that's going to be an open circle. So write an open circle at (-1). There is my graph. There it is. That's it. Here's the graph again. And when we take a look at number 9, we start talking about domain. So it says the domain of a piecewise-defined function consists of the union of all the domains of the individual pieces of the function. Likewise, the range of a piecewise-defined function consists of the union of all the ranges of the individual pieces of the function. You can represent the domain and range of a function by using inequalities. You can also use interval notation and set notation to represent the domain and range. So what I did is just give you this first type of graph to find the domain and range, and then we look later, and then afterwards we look at the piecewise-defined function. So really quick, let's go through this example right here. If I wanted to find the domain and range, I have to look at each one individually. So let's look at the domain. And when you're looking at the domain, you're only focusing on the x-axis. And so that's the only axis you have to look at when you're talking about the domain. And so what I did is I got rid of the y-axis, and I had you write this. The domain, you're always looking at the x-axis. And I also had you write this. To find the domain, you're just strictly focusing on the x-axis, and we're going to use horizontal moving elevator doors. Now, this is a new concept, but one that I like to use. So I'm going to create my elevator doors, and notice that these elevator doors only move horizontally. That's why they're horizontal moving elevator doors. Now there's something special about these elevator doors. They only open up enough just so that you can squeeze inside, not even a micrometer more. And so only just enough so that you can squeeze through. But instead of you squeezing through, we want the function to just squeeze barely through. Alright. So the first form, we're going to write the inequality of the domain, the inequality form. And since we're talking about the domain, which is on the x-axis, we use the variable x that goes in the middle. And this is something important. On the left side is going to be your smallest value, and on the right side of that x is going to be my largest value. So let's begin to find the domain. Remember, I'm going to move this left elevator door, and I just want to open it enough just so the graph can squeeze through. So I had one of my students tell me when to stop, and he told me to stop right there. And I asked that student, tell me at what value did that elevator door stop? Well, it stopped at -6. And is -6 going to be my largest or my smallest value of my domain? It's going to be my smallest value. And so I write -6 on the left side. Now here's something important. Do we have a closed or open circle at -6? And we see that we have a closed circle. So going all the way back to my chart, if I have a closed circle, that means I'm using. Now there's something about the way we set this up. We're only going to be using either less than or equal to. We don't have to worry about these for the domain because of the way we have it set up, where our on the left we have the smallest value, and on the right we have the largest value. Because we have a closed circle, that means I'm going to be using less than or equal to. Less than or equal to. Now let's go ahead and move the right elevator door, and I want to only move it just so that my graph can squeeze inside. And when I do that, notice that it stops right here. So the student told me to stop here, and I asked that student what x value did it stop at. It stopped at 7. So here we have 7. Now what I did is I told my students, this is an open circle. I want this to be an open circle, not a closed circle. I just changed it up just so they can get familiar that we are going to have open circles as well, not just closed. And I told my students, well, what inequality am I going to put in between the x and the 7? Because I have an open circle, I'm going to use less than. Again, don't worry about greater than or equal to, because of the way our inequality is set up, where the smallest goes on the left and the largest goes on the right. So that means I'm going to use less than. Alright, there we go. That is the domain. We just found the domain. By using elevator doors and looking at the x-axis. So here's our original question. To find the domain and range, we have to use all three notations, so we're going to come back to this in order to find out how to find the set notation and the interval notation. But right now, let's go and look at the range. Now the range, we're not going to look at the x-axis anymore. That's just for the domain. We're actually going to look at the y-axis. And so what I did is I took away the x-axis, got rid of it, and I had you write this. Range, you're just looking at the y-axis. And along with our looking for the range, we're going to be using vertical moving elevator doors. So again, the reason I call them more vertical moving elevator doors is because they move up and down. And the reason, and again, these elevator doors are special because they only open up enough just so that the graph can squeeze through. So we want to start with our inequality form again. Inequality. Since we're using the y-axis, we're concentrating on the y-axis, we use our variable y. And just as we did with the domain, our smallest value is going to go on the left and our largest value is going to go on the right. If we want to find our smallest value, we need to move the bottom elevator door and see where it stops at. So again, I had one of my students tell me, I'm going to move this elevator door down and I want you to tell me, when should I stop? Just enough so the graph can squeeze through the elevator doors. Alright, and I said, are you ready? Yes. Alright, let's go ahead and get started. So I moved the elevator door, I moved it, and then some students were saying stop, but nope. And there, that's where it stops. And I asked the student, what value did it stop at? -7. Is that my largest or smallest value? Well, that's going to be my smallest value because the other door, elevator door, moves to a positive value. So here, I'm going to write my smallest value. Which is -7. And I asked the student, what inequality am I going to put in between -7 and y? Well, remember, because of the way we have it set up, where the smallest goes on the left, the largest goes on the right, we have to use either one, less or less than or equal to. Since we have a closed circle, it's going to be less than or equal to. Now remember, we made this be an open circle. And so, just to remind you that, I reminded my students that. So I said, okay, I picked another student and I asked that student, I'm going to move this elevator door and I want you to tell me when to stop. Are you ready? Student said yes. And so I said, let's go. And the student said stop. And I asked my student, where did it stop at? It stopped at 5. And again, I remind my student, this is an open circle. So if this is an open circle, what inequality should I use? And the student correctly said less than. And that's it. That is my range in inequality form. By using vertical moving elevator doors. So my function is able to squeeze through and move on with its life. Alright. But now the book is asking not just for inequality form, it's also asking for the set notation and the interval notation. So let's go back to the domain. Set notation is actually very simple. What you need to do is, first thing you need to do is draw your curly braces and open and closed. Since we're talking about domain, we're using the variable x, and we use this vertical line right here. This vertical line means such that. So the vertical line means such that. Same thing we're going to do for the range. I'm going to draw my curly brackets or a brace. I think the formal definition is a brace. My variable is not x but y for the range, and again I draw this vertical line, which means such that. So as you can see, the setup is always going to be like this: curly brace, x, such that, close curly brace. Same thing for the range, except the variable is y. And what is going to go in here? What is going to go in there? Well, it's actually going to be the inequality. Simple as that. -6 is less than x, which is less than 7. Here it's going to be -7, which is less than y, which is less than 5. That's it. So the set notation is actually the inequality, except you're adding this extra stuff around it. That's pretty much set notation. Alright, and finally we need to find interval notation, and there's something I have to add to my interval notation, to my graph here, my chart. For interval notation, I guess I'll write interval here. If I have less than or and open circle, I'm using parentheses. If I have less than or equal to and close circle, I'm using square brackets for my interval notation. Okay, first thing I want to do here for my interval notation is take my smallest value and put it on the left, comma, and I'm taking my largest value, putting it on the right. Now, because at the -6 I had a closed circle, and my inequality between the -6 and the x was less than or equal to, closed circle, that means I'm going to use a square bracket only on the side of the -6. There we go. Now, am I going to use close bracket here? I don't know. I'm not sure yet. So let's look at where 7 is at. 7, I have an open circle, and in my inequality I had less than between x and 7. So I have less than and I have an open circle. That means I'm going to use parentheses. So on the side of the 7, that means I'm using parentheses. So it doesn't have to be square brackets or parentheses on both sides. I mean, it doesn't have to be parentheses on both sides, or it doesn't have to be square brackets on both sides. It can be a combination of one or the other. So in this case we have square brackets because we had less than or equal to here, and here we have parentheses because we had less than right there. And that is it. That's my interval notation for the domain. Interval notation for the range, again, I'm going to take my smallest value, comma, largest value. And because I have less than or equal to and a closed circle by the -7, that's going to be a square bracket. And because I had an open circle and a less than on my 5, I'm going to use parentheses. And that's it. That is the inequality set and interval notation for this function. There we go. We found the domain and range. Alright. Now let's go back to number 9. Write the domain and range of g of x in items 5 by using inequalities, interval notation, and set notation. So when I graphed this is what I came up with right there. Here's a better graphed form right here. Same thing for item number 5. Alright, so the first thing we want to do is find the domain, and then we want to find the range. First form we want to find it in is inequality here. Alright. So remember, for the domain, I'm looking at the x-axis, which means that my inequality form, I'm going to use the variable x. And I'm going to use horizontal moving elevator doors. So here's what I want to do. I'm going to move this elevator door to the left, and I asked my whole class together, tell me when to stop so that the function can squeeze inside. Alright, are you ready? Yes, let's get started. Stop. My students said to stop here. And then some of my other students said, no, don't stop, keep going. And so I asked them, should I stop here? Why should I stop here? Tell me why. And then my students were able to figure out, no, you don't stop there. Why don't I stop there? Because it has an arrow. And what this arrow means is that it just keeps on going and going and going and going. And so does this elevator door also keep on going and going? If this line keeps going to the left, that means my elevator door keeps going to the left, going to the left, going to the left. Is it ever going to stop? My students realized, no, it's not. It's never going to stop. So how do I know what value what value to put here as my smallest value, since we're talking about negative numbers? What should I put on my left side? If it keeps on going and going forever, how do we represent that? Infinity. Infinity. I think that's a good idea. Infinity. But we're talking about negative values, right? Does it make sense to use positive infinity? No. Use negative infinity. Yes. That is it. That is going to be my smallest value. But then I asked them, well, if I have negative infinity, what am I going to put in between the negative infinity and the x? What inequality should I use? Well, okay. Well, one of my students said, well, use less than or equal to. Maybe that works. And then I asked my student, what problem do I get whenever I put less than or equal to? What does that equal to mean? You're telling me that there is a number that equals negative infinity? No. so it's going to be less than. And so that's going to be the general rule. If you have less than, if you have infinity or negative infinity, always use less than for inequality. For inequality notation. If you have infinity or negative infinity, always use less than. Not less than or equal to, it's always going to be less than. Alright. And so, then I asked my class, well, where am I going to stop this one then? Alright, let's go. So I started moving my elevator door and told me to stop here. Right here, why should I stop here? Well, because that's where the graph ends. This graph ends right there, so you should stop right there. But then I told my students, well, do you remember when we saw the notation for this? Even though we have two function rules, did we have just one name for it? We counted them all together as one. And so when we're looking at the graph, we're looking at the whole graph as one. This is not an individual part, and this is not an individual part. They are all together. And so if I stop here, the whole graph is not going to go through because this other side of it is not going to be able to squeeze in. It's the elevator door is blocking it from squeezing through. And so then my students realize, well, you keep on going then. Keep going, keep going, keep going, keep going. And still I had some of my students say stop here. And I asked that student, why should I stop here? Because that's where it ends. But tell me, what does this arrow mean right here? Well, that arrow means that you keep going. And then that student realized that it keeps going and going and going. And the student told me to keep moving, keep moving, keep moving, keep moving. And eventually, we realized that the elevator door never stops. It just keeps on going to infinity. Positive infinity. And so I asked them, well, what inequality should I use in between the x and the infinity? Well, you always use less than. That's it. That is it. That's my domain right there. Okay. Alright, so I'm just going to jump into the range. For the range, I'm going to be using the y-axis, which tells me I'm going to use the variable y for my inequality. And I'm going to be using vertical moving elevator doors. So here are my elevator doors. Alright. First thing I want to do is find my smallest value, which goes on the left. So I asked my students, okay, are you guys ready? Tell me when I should stop moving this bottom elevator door. And so we kept on going, and some students said stop here. And the student realized, nope, you don't stop there because this bottom part of the graph is not going to be able to go through, so you need to keep on going, keep on going, keep on going, keep on going. Okay, stop here. Now, why do I stop here? Don't I just keep going down? Well, there's no more graph at the bottom of that, so that means that my elevator door is going to stop right here, right there. Now, what value is that? Don't say -1. What are we looking at here? We're looking at the y-axis. So what y value does it stop at? It stops at y equals 0. So my smallest number is 0. And notice here we have an open circle. So what inequality am I using? Open circle, I use less than. Alright. That's it. Alright, let's do the top elevator door now. So we're opening the door, We don't stop there. Keep going, and then some students say stop here. And again, I told them, why do we stop there? Well, that's where the graph ends. But what does the arrow mean? Well, the arrow means it keeps on going and going, and finally the light bulbs went off, and they realized that, well, you're never going to stop, so that means you're going to infinity, positive infinity. And what inequality should we always use with infinity? Well, it's always going to be less than. That's it. That's all we have to do. Next thing we had to do was set notation for both of these. Alright. Remember, set notation, we have to use our brace. So let me set up my brace. And I'm going to use x such that, and here for the range is y such that, and then you can just put in the inequality. Negative infinity less than x less than infinity. Here would be 0 is less than y, which is less than infinity. Now there's actually a different way. Since we have negative infinity to infinity, there's actually a different way we can write this. We can write this as x such that x is an element of the real numbers. What is this saying basically? Well, it's saying that all the numbers are my domain, from negative infinity all the way to positive infinity. So since all my numbers are in my domain, this is what you're going to, this is what the book uses commonly. It's going to be, my domain is x such that x is an element of the real numbers. That's it. Here we could also use a different thing. We can use y such that y is less than infinity. Well, no, not that. Y is greater than 0. Both of these are the same thing. And usually the book does not like using infinity in its set notation. Instead, it uses this right here. And notice these two are exactly the same thing. And so it's very important to notice that if 0 is less than y and it's less than infinity, is the same thing as y is greater than 0. Because, can you see that we have y greater than 0 here? Why do we not? Do we actually need infinity there? Well, if we say that y is greater than 0, what numbers are greater than 0? 1, 2, 3, 4, 5, 6, 7. And do you see that you can actually keep on going? 5, 100, a billion, a trillion. Google, which is a number with 1 and 100 zeros. You can keep on going to infinity. So this implies that you go to infinity, and set notation likes using this form right here. Alright, finally we need the interval notation. Interval notation. Again, we're going to take our smallest value, write it on the left, take our largest value, write it on the right. Because we have less than, going all the way back to my chart, if I have less than, I'm going to use parentheses. And notice I have less than on both sides, here and here, so that means I'm using actually here and here, which means I'm using parentheses on both sides. That is my interval notation. For my range, my smallest value is 0. My largest value is infinity. Separate them with a comma. Notice again I have less than and less than on both sides, so that means I'm using parentheses on both sides. That's it. That is going to be the domain range of our piecewise defined function. Did I have anything left here? I had you get some more practice on number 10, A and B. I also want to point this out. Okay, I guess it's not letting me. Let me pause. Alright, one last thing I want to mention is on page 60, you have those symbols that we used for domain and range. Again, the notation for a vertical line means such that this E looking symbol, this means elements. The R looking symbol is the real numbers. Z is the integers, and N is the natural numbers. So mainly these symbols are used for set notation. Alright, thank you for watching.